Welcome back to my Calculus Conundrums applications of derivatives, and we're going to talk about Extrema here, and make sure you subscribe if you find these helpful. Extrema, that just means for the highest and lowest points. So for instance, in a graph we can have what's called relative extrema, or we can have absolute extrema. So relative extrema are just those points that are highest in their neighborhood, but absolute extrema is would represent the highest or lowest point anywhere on the graph. And many times you won't have absolute extrema for a particular graph, because a lot of times your graph will maybe look something like this, where it goes down infinitely and it goes up infinitely. And so therefore there would not be an absolute extrema, since it decreases without bound and increases without bound. But you would see here you got a little peak here and a little valley here, so those would be the relative extrema. Okay, so but let me just talk about the extrema, which this right here is talking about absolute extrema. It says let f be defined on an interval I containing x equals c. F of c is the minimum, and when we say that, we mean absolute minimum of the function f on I if f of c is less than or equal to all other functional values. In other words, if f of c is less than or equal to all other y values, then we would say f of c is the minimum. Now, if f of c is greater than or equal to all other values on the interval, then we would say f of c is the maximum of f. And so, as I said, the minimum and maximum functional interval are the extreme values, or extrema, of the function on the interval. And these minimum and maximum values on an interval are called the absolute minimum and absolute maximum, and some books call them global minimum and global maximum. So I just want to first show you absolute maximum. So if you looked at this graph right here, and we're going to pretend like this graph is stopped. So this graph stops right here. It doesn't go on forever and ever, okay? Alright, so I put little dots there so you know it stops. So if we just got this portion of this parabola, then we can see that the lowest point is this point here, 5, -7. And since the y value is that minimum, the minimum would be -7. So the absolute minimum of this graph would be -7. Now, the absolute maximum, that would be the point. I tried to do this to scale. Go 1, 2, 3, 4, 5, 6, 7, 8. So the actual maximum would be 8. And actually it occurs at 2 points. It occurs here and it occurs here. I should have labeled these, but just understand that these both represent absolute maximums, even though they're the same number. So you get y equals 8 here. Okay? Actually, don't even worry about what the points are. Just try to understand that these points represent the absolute maximum value of this graph, and this point represents the absolute minimum. I'm afraid I don't have it labeled for you, so that's going to be confusing. So let's just focus on the graphs themselves. So let's take a look at this graph. And again, pretend like this graph stops here and stops here. In other words, it doesn't go on forever and ever. Alright, well now if we look at this graph, you'll see that the highest point appears to be right here. So that point would give us the absolute, that would be the absolute maximum, and the lowest point appears to be right here. So this point would be the absolute minimum. Okay, now this point here, even though it's not an absolute maximum, it actually would be a relative maximum, because it's the largest value in its neighborhood. Okay, and so we'll talk about relative maximums in a moment. Now, I drew some graphs here and tried to show you, to help you understand things a little bit. Earlier we looked at this graph and we found that we had a critical number of -1. At -1 we get a critical number, and at +1 we get a critical number. Well, notice that the derivative would be 0 at -1 and +1, because you get the horizontal tangent lines. And also notice that you get what's called a relative max. You get a relative max. In other words, the maximum in this neighborhood, you get a relative maximum at -1, 2, and then you get a relative minimum here at 1, -2. So these are relative extrema. Now on these graphs, you know, it does continue on in each direction. Okay, now you remember this one? We looked at it in a previous video. So notice here, these 2 points here represent points where you get a relative minimum. This is the lowest point in its neighborhood, and this is the lowest point in its neighborhood. And then here at 0, when x is 0, you get a point here. That's the highest point in its neighborhood. So there you would get a relative maximum. And then here, now here, remember a while ago we said this was a critical number? Okay, well, just because you have a critical number, it doesn't mean you're automatically going to get a relative maximum or relative minimum. This one here has no relative extrema, but even though that is a critical number, we have no relative extrema there because, you know, the graph comes up like that. Now, see, if it had come up like that, and then if it had turned around, let me see if I can show you. If it had come up like that and then turned around and headed back down, then this would be a relative maximum. But it didn't do that, did it? It just kept increasing. So therefore, there's no relative extrema there. So really, what I'm trying to what I'm showing you these graphs for is to show you that in order to have a relative minimum or relative maximum, they must occur at a critical number. So just like this maximum occurred at this critical number, this maximum occurs, this minimum occurred at that critical number, these minimums occurred at these critical numbers, and this maximum occurred at that critical numbers. But just because you have a critical number doesn't mean that you're going to get a relative maximum or minimum. Okay, so let's talk about the extreme value theorem. The extreme value theorem is the theorem that guarantees that we get an extreme value within an interval. So if f is continuous on the closed interval from a to b, then f has both a maximum and a minimum on the interval. So if you tried to draw any continuous graph from 2 points, you couldn't draw it without having a minimum and a maximum on the interval. So here, let's take a look at a couple of examples. Consider this graph, but only on the interval from 0 to 7. So just pretend like that's not, this part over here is not there. Alright, so we go from 0 to 7, and this part out here is not there either. Okay, so we're only going from this point to this point. Now, the extreme value theorem says that I have a minimum and a maximum on this interval from 0 to 7. So notice where the maximum is. The maximum is right here at this end point. It's at the end point of the interval. 7 is the end point of the interval. But the minimum is actually here. And this is where you would get a critical number. Okay? So to find the absolute extrema for this function on 0 to 7, you would check the endpoints and see at 0 you get 0 and at 7 you get 49, and then you would check any critical numbers. So here at critical number is 4, and at 4 you would get negative 32. So after you check the y, see what the y values are of your endpoints and what the y values are of your critical numbers that fall within that interval, then you determine which one's the largest is your maximum and which one's the smallest is your minimum. Okay? Now, so here the maximum occurs at the endpoint and the minimum occurred at one of the critical numbers. Now on this one, you'll notice I'm looking at it from -3 to 7. So you'll notice that this one, the minimum occurs here at -3 and the maximum occurs at 7. Now, so these are the absolute extrema. This would be the absolute minimum. This would be the absolute maximum. Now, are there any relative extrema? Yeah. This point right here is the highest point in its neighborhood, and this point right here is the lowest point in its neighborhood. So, but the absolute extrema would be at these endpoints. Okay, now let me go ahead and give you a definition for relative extrema. It says if there is an open interval containing C on which f of C is a maximum, then f of C is called a relative minimum. Basically, that just means that as long as there is a neighborhood where f of C is the largest value, then f of C is called a relative maximum. And likewise, this one says as long as there is an interval where f of C is a minimum, then f of C is called a relative minimum. So if you go back and look at this graph here, you'll notice that there's a peak right here, and so there's certainly a small window here. Well, there's a window here, I should say, about -2, where -2, 0 is the largest value, and there's a window here about 0, where the point 0, -4 is the smallest value. So these would be relative minimum. Now, the actual maximum is the y value. So the maximum here is 0, and the minimum here is -4. I know those are small, but the minimum and maximum are the y values. So usually, if you're going to define the minimum or maximum function, you give the y values, but you never give the x values, so the maximum. You can say that that's where they occur. Like I can say that x equal -2, like x equal -2 is where this maximum occurs, and I can say at x equals 0 is where this minimum occurs, but 0 and -2, those are not the extreme values. The y values are the extreme values. Okay, look at this one. Here I get a minimum, a relative minimum at x equal -3 of 3, and here I get a relative minimum at x equals 6 of 3, and here I get a relative minimum, maximum. I get a relative maximum here at 1.5, which is roughly 10.429. So I just rounded the answer there on that one. So anyway, those are some examples of relative maximums and minimums. So this video was really just to introduce you to what absolute extrema are and what relative extrema are. Now let me just summarize here again. Like for instance, if let's say this graph stopped at these points, okay? If this graph stopped at these points, then these points would be your absolute maximum. These would be the absolute maximum value because they're the highest points on the graph. And these points would be the absolute minimum. They're the lowest points on the graph. Now, an absolute minimum can also be a relative minimum. So they would also be relative minimum because they're, the minimum values in their neighborhood. Okay? This one would only be a relative maximum. It certainly wouldn't be an absolute maximum because you got values higher. Now, if I take these away, and I let this graph just continue in these directions like that, like they normally would, then this has no relative maximum because it increases without bound. Now it still has a relative minimum, but it has no relative maximum. Likewise, over here on this one, you see the relative extrema. We talked about this point and this point being relative maximum and relative minimum. But let's say the graph stopped at this point and this point right here. Well, then this right here would be your relative minimum because that's the lowest point. I'm sorry, that would be your absolute minimum because that's the lowest point. And then this would be your absolute maximum because that would be the highest point. So if it did stop, then you would have an absolute minimum here, absolute maximum here, and then these would be relative maximum and relative minimum. Now, if it didn't stop, if it just kept going in both directions, then in that case, what would happen is you would have no absolute extrema because this decreases without bound, this increases without bound, but you would still have these two relative extrema. So this would still be a relative maximum and a relative minimum. So again, this video was really just to kind of help you understand what absolute minimum, maximum, relative minimum, maximum are. And in the next video, we're going to apply what's called the first derivative test that's used for finding relative extrema.